As we have maximum yes for this video, we will discuss the wind turbine placement problem in Python. So objective is here the optimal placement of wind turbines in the wind farm so that it will generate maximum electricity at minimum cost. We already discussed the optimal placement of wind turbines using particle swarm optimization algorithm in this video. For more details, you can check this video. Right now we will implement this problem in Python, that is the optimal placement of wind turbines using particle swarm optimization algorithm. So first we will discuss the key points about this problem. After that we will start the implementation part. So we'll just discuss the key points. For more detail you can check this video. First we have wind turbine. As we all know, wind turbine is a device that converts kinetic energy from wind into mechanical energy that we can use to generate electricity. Here you can see different components for the wind turbine, like generator that is mainly responsible to convert the mechanical energy into electrical energy. Then we have hub, that is the central part of the wind turbine, and other parts you can see here: tower, gearbox, blades, and main shift. Next we have wind farm, that is also known as wind power plant. Wind farms are situated in areas having continuous and strong wind patterns to generate more electricity, and we can locate multiple wind turbines in wind farm, range from 4 to 100. It depends on the wind farm size and its capacity. Next we have different wind farms: small scale, medium scale, and large scale wind farm. Small scale wind farm consists of wind turbines less than 10. Medium scale wind farm consists of dozen to few dozen wind turbines, and large scale wind farm projects can have 100 or more wind turbines, depends on their size and capacity. Next we have Bake effect. It reduces the wind speed and increase turbulence. Next, for the wind turbine placement problem, we have different factors that should be keep in mind for the optimal placement of wind turbines so that it can generate maximum electricity at minimum cost. First, identify suitable area for the wind farm that have continuous and strong wind patterns, and also keep in mind the construction and the maintenance cost for the wind farm. Then we need different wake effect control strategies. Next we have wind farm layout optimization, and also choose the appropriate model for the wind turbines so that it can generate more electricity. Our goal is here maximize the energy production at minimum cost, and also minimize the bake effects so that we can generate more electricity and we can maximize the efficiency. Also keep in mind to minimize the environmental factor like noise. Now we will start the implementation part. So we will implement this research paper, that is the optimal placement of wind turbine in wind farm layout using particle swarm optimization algorithm. In this research paper, for wind farm layout optimization, different strategies are used, that is 3-step strategy and the particle swarm optimization algorithm. Here in this video we will use just particle swarm optimization algorithm for simplicity, and to improve results you can add other methods, like here they added the 3-step strategy. For better results you can add other method. Right now we will just use PSO to solve this problem. 3 case studies have been performed. First case, there is no wake effect. Second case, we have bake effect. Third case, there is partial wake effect. So next we have here Jensen-Bake model that we will use here in this video. So first condition, we have no wake effect. Then you can see the mathematical equation. Second we have wake effect, and you can see this is the equation that we will use to calculate wake effect. A, that is the axial induction. Alpha is constant. Capital X, that is the distance between two wind turbines. R1, that is the downstream rotor radius. Next we have alpha calculation. Then we have partial wake effect calculation. Here this is the partial rotor area under wake effect, and this is the total rotor area. Then we have another case, that is many wake effect, and you can see the mathematical model for this. Then we have power calculation. Here you can see we have different cases for the power calculation. So we have the virtual environment, so we'll use different virtual wind speed values. Then we will calculate the final output. Then you can see here, this is the annual energy production that we will calculate using this. Here 8760 is considered as the total hour in 1 year into total power that is calculated. Here this is the ideal power and this is the virtual power. Then we have total power, that is ideal plus virtual. Then the annual power is calculated by 1 year into total power. Next we have efficiency. So in the end we will calculate the cost, and then we have the objective function. Here we need the minimum value, the cost divided by total power. Now we will start implementation. So this is the simple flow chart for this problem. First we will initialize all the parameters for the wind turbine, wind farm. Then using objective function calculate the maximum power output. Then we have PSO parameter, big model calculation. Then we will calculate the new power output, and then we will compare the new power output with the older one, and then we will check if the minimum power obtained or not. If condition is true, then stop and display the best solution, else we will repeat the loop until the stopping criteria is met. First we will import all the libraries. First we are using here NumPy to perform the numerical operations for the mathematical operations. Random, that we will use in the PSO for the randomness. Now we'll define the function here. First we have probability distribution function. So first define this function. Function name we have PDF. You can see the equation for this function on the screen here. I have on the paper. So this function have different input parameters U, K and C, and it will return. Apply this now. Just write this equation here. K divided by C into U divided by C, its power K minus 1 into, we have exponent minus U divided by C, its power K. Done. Done. So we have first function, that is the probability distribution function. Now we will calculate alpha. Again you can see the equation here. So define a function. Function name we have here, calculate alpha. We have, for this we have two parameters, hub height and the surface roughness, and 2. Done. And this function will return, enter the equation here, 0.5 divided by math.log, then hub height divided by the roughness. Now we have next function, that is calculate wake effect. So define a function again here for the wake effect. So first we will calculate here full wake effect. So here we have full wake effect. This is the function name, full WE, that is the full wake effect. Now we have different input parameters for this. You can see in the equation here we have U0, that is the wind speed, A, then we have alpha, next we have distance between two wind turbines, rotor radius. This function will return, enter this equation here, that is u0 into 2 into a, that is divided by 1 plus alpha into x divided by r1, x divided by r1, its power we have 2. Here this is 1 minus 2a divided by this. So this is to calculate full wake effect. Now we will calculate partial wake effect. So again define a function, that is partial wake effect. Again we have different input parameters, wind speed a, alpha, then we have distance between wind turbines r1, then here we have a partial and a total wake effect. This function will return, so enter this equation here. Now it is u0 into again 1 minus 2 into a divided by 1 plus alpha into x divided by r1, its power we have 2 into a partial minus a total. So now we will define the value for all this. Define main k is value we have 0.10. You can check all the values in the research paper. For C we are using here 10. Next for hub height, capital G, that is the hub height, it is 60. Z0 rough surface roughness, that is 0.3. A we have 1/3. u0 is 12, that is the wind speed. Next we have suppose the distance between two wind turbines is 200, and we used here d, that we will use later. Radius, rotor radius 40, rotor radius we have 40. The value for r1 that we used here, you can see the r1 is a into x into r. Next we have, so we will calculate alpha using this function. Next we have this a partial and a total. That is, then for a total first we will calculate a single, that is 3.14. We have a total, that single. Third case we have no wake effect. So for this define a function, no wake effect. We have just constant wind speed and it will return this. Now we will calculate power. So define a function here for the power. We have parameters like u, and we have ideal power. So we are using here this equation. So first condition is u. If u is less than 3, suppose wind speed is 3, then it will return 0. Next, else if value for u is greater than or equal to 3 but it is less than equal to 12, then return this value, that is ideal power. Then return the ideal power. Next case, else if u is greater than or equal to 12 but it is less than equal to 25, then return this value 518.4, else return 0. So this is for the power calculation. Now we will calculate objective. You can use different equations, it may be little bit different. So now we'll define the objective function here. So first define objective function. Objective function name we have this. Input parameter like installation cost, ideal power, then we have wind speed values that we are taking as u value, k and c, and here we will calculate the objective value is equal to installation cost divided by total power into this function that we define here, PDF. We have PDF and have different parameter like u, k, c. For u in u values, here we have total power. Now done. So this function will return the minimum value of the objective function. So it will return this minimum value. Done. So now we define here all the cases for the wake effect, for the power calculation, and we define here the objective function and different values for all this. So now we will apply here PSO. So first we will initialize PSO parameters. Population size, suppose we have here 100, maximum iteration suppose 500, and you know PSO algorithm we already discussed in Python also. PSO algorithm we already discussed. For more detail you can check this. So for PSO algorithm we have the inertia value, that is, so for work inertia value 0.5, coefficient C1 2.5, C2 is also 2.5. So here we have a class for the particle. So here we have the agent's position, their velocity and all, self position. Position as randomly initialized. So we have random, uniform, and the value we have here 0.1, 0.1, then we have random, uniform. Here we have, so here we use just this value, you can change this accordingly. These are just the example values. Next we have velocity. So here we randomly initialize the agent's position in the search space. Now initially their velocity is 0. Now their personal best values, you know, the p best value is also the copy of their position, position dot copy. Main loop for PSO. So first we have the main function for this config. Here we will create a dictionary for the values that we will use in the calculation in this algorithm. Initial total power is config total power. Next we have wind speed values. Here this is the wind speed value, that is configure this value here. So let's define the wind speed values here. So here we have wind speed values that are u values. Here we have 3, 9, 6, 9, 12, 15. Next we have k, that particles, that is equal to, we will access the particle from the class. So particle for in range up to the population size. So here the G best, that is the global best, is the particle at best position. So we are accessing here the best position using the agents. So global best we have dot p best dot copy. So here we have this particles will access. Best of A is G best at 0, that is the best value. This is G best. Best installation cost G best 0, and we can calculate installation cost is equal to this formula we have, population size into 2 by 3 plus 1 by 3 into math.exp. Then here we have this minus 0.00174 into population size. So suppose we are considering this for the 2 wind turbines. Next, so now we will start here the loop, that is for the PSO. So for iteration in range, that is we have maximum iteration, we repeat the loop until the maximum iterations. Maximum iteration we have 500. So for each particle we will update their position, calculate this value. So for each particle we will update their position, calculate the witness values, that is its position. So we will access initially by the agent's position. We have total, so we are using here the particles, that is the search agents, to calculate power. This is initial total power and wind speed. Check the best value. Now we will apply here the objective function. objective function that we have here. So we'll use this objective function and its all parameters. So what here we installation cost and the total power, particles, wind speed value. Next we will compare P West and G West. So first we will compare P West to check if the objective value that we obtained here is less than. Here we have the objective function, but here we will compare the particles P West position. If this condition is true, then the position copy. We will compare for the G West. Again we will compare here. So again compare here with this, but here instead of this we have the global West value at 0 total. So if this condition is true, then G West would be that position and the best of A would be the best value, and then the best installation cost is the installation cost. Now we will calculate velocity for each particle and then update their position. So here for I in range up to the length of particle dot velocity, this is length. You can see the equation. In this equation we have two random number r1 and r2. Initialize the two random number, that is random dot random, first random number. So here we use a library that is import random. We have cognitive and social velocity. First we have this velocity, that is c1 into r1 into personal best same for social velocity. We have here c2, and velocity is calculated as inertia into the particle previous velocity plus the cognitive velocity and the social velocity. Now the velocity is calculated. Now here we will calculate position. So the particle position here will best installation cost and the best value. First we have ideal power, that is (0.3 into u0 constant wind speed power 3). Done. Next we have actual power. A partial power calculation. So the total power is equal to ideal power plus the actual power. Next we have an annual energy production calculation, AEP, that is. Next we have again a dictionary for the values that are used in PSO for the calculation. Here we have a partial and a total. installation cost, and here we have configuration. Use all the values from here. Done. Then the best objective value, we have best using this function. Call the function here. Installation cost, here we have the best installation cost. Then total power, wind speed value we will use here as C, that is equal to total power divided by 2 into ideal power. And finally we will display output values. So here first we will print objective value that is stored in the function. Next we have efficiency that is stored in this variable. The last one we have total power that is stored in this variable. Then run the file. Here we will apply this partial wake effect. So we have error, this equation is not written as 2y3 plus this one, and here. Now run. Now you can see here we have the objective function value that is 0.15840, efficiency that is 50%, total power we have 518. So we can further improve the results by improving the equations. So we calculated the objective value, efficiency and total power. For better results, we can combine different methods for the optimal placement of wind turbines. Plus, when you're writing the equations, write accurately so that it will provide us accurate results. So that's all about this video. If you have any questions, you can comment below, and thanks for watching this video.